Hello everyone, welcome. So for this problem, what we are asked to do is to find a general solution to the following ordinary differential equation, x squared plus 1 times dy dx plus xy minus x is equal to 0. Now the method that we are going to employ in order to solve this differential equation is the method of integrating factor. Now, in order to use the method of integrating factor, the first thing we have to do is we have to put our differential equation into what's called standard form. Now, standard form looks like this. We have the dy dx on the left-hand side plus a function p of x times y, which is equal to another function called q of x. Now, as we can see, our original ordinary differential equation is not in this form. So we could do a little bit of algebra to put it in what's called standard form. Now, the first thing we're going to do is we're simply going to divide by the x squared plus 1 term as such. And now what we could do is we could move the third term over to the right, and we have this equation here. Now, if we compare the equation that we're working on to the standard form, we can see that we have manipulated our original differential equation to correspond with the standard form of linear differential equations. Now, the reason why this is important is because we're going to be focusing on this p of x term highlighted in green over here. Now, the reason why this p of x term is important is because we use this to define what's called an integrating factor. And this integrating factor is going to have the symbol mu. Now, mu is defined as such. We simply use this p of x and we use it for our definition of mu. Now, the integrating factor is simply defined as e to the exponential integral p of x dx. So what we can do is we can use this definition and use our p of x to simply just evaluate and obtain what the integrating factor would be. And that's done by simply evaluating this right here. Now, what we're going to do is we're going to switch the, notation a little bit, and we're not going to use the e to the power. Rather, we're going to use the exp, which is essentially the same thing, but it's just easier to visualize and look at, especially if we have a lot going on in our exponent. Now, in order to evaluate the integrating factor, it seems like we're going to have to obtain the antiderivative of x over x squared plus 1. Now, we can't really think of an antiderivative right off the bat that we could apply over here, but it seems like we're going to use some kind of a u substitution. So what we're going to do is we're going to simply define u to be equal to x squared plus 1. Now that we've defined u as x squared plus 1, we could take the derivative of both sides, and we see that du dx is simply equal to 2x. So now we have a u, and we have du dx. Now we could do a little bit of algebra to manipulate the du dx definition and have dx in terms of du. Great. Now we have u and we have dx. Now the next thing we're going to do is simply substitute in our definition of u and definition of dx as such. Great. Now we could do a little bit of algebra and we can divide out the x's as such, and we can pull out the 1/2 like this. Excellent. Now, what we have here is we have the integral of du over u, which should be a fairly easy antiderivative to just recall. The integral of 1 over u du is simply just ln of the absolute value of u. Great. And what we could do now is we could apply the rules of logarithms, and we see that this is the same thing as ln absolute value of u to the 1/2 power if we use our rules of logarithms. Excellent. Now what we could do is we see that when we have an ln that's raised to an exponential, the exponential and the natural logarithm cancel out as such. And let's not forget to plug in our definition for u like this. Great, so we're almost there. Now we're dealing with the absolute value, the absolute value of x squared plus 1. Now what we have to remember is the plot or the function x squared plus 1 is really never going to be negative ever. So the absolute value of x squared plus 1 is simply going to be the same thing as x squared plus 1, because this function can never be negative because you're squaring a number which will never end up as negative, and you're adding 1, so your number will always be positive. So we could drop the absolute value and just switch it out with parentheses. Great, so we're almost there. We've defined our integrating factor, and now we want to refer back to our original ordinary differential equation. And what we could do is, the next step now is to take our integrating factor, and then we're going to multiply the integrating factor throughout our ordinary differential equation as such. Excellent. So we're simply just taking mu and we're multiplying the entire equation by mu. And let's not forget about the definition. The definition of mu is here, or I guess the integrating factor that we evaluated from the definition is x squared plus 1 to the 1/2 power. Great. Now what we're going to do is we could simply just do some very straightforward algebra, and we see that we could divide out the x squared plus 1 in the denominators with the x squared plus 1 to the 1/2 in the numerator, and we end up with x squared plus 1/2 in the denominator. Excellent. Now, this part's really, really important, and I think it's the part in the process that most students struggle with and have a difficult time analyzing. If we pay attention to the left-hand side, if you went about this method correctly, the left-hand side will always, always, always simplify to, or I guess can be written as d dx of the product of the integrating factor times y. This will always, always, always happen if you evaluated your integrating factor correctly. If your equation was originally in standard form, you extracted the p of x, and you evaluated the integrating factor correctly, the left-hand side will always, always come out to d dx of mu times y. And you could double check this yourself by simply just taking mu, multiplying it times y, and taking the derivative with respect to x, and you apply product rule, and you should see that you should get the same thing as the left-hand side always. Now, this is always going to be true if you did the problem correctly, and we could simply replace the entire left-hand side with d dx of mu times y. Now, we could apply the separation of variables here, and we simply move the dx over. Then we have d of mu y, which if we integrate, it's a pretty straightforward integral on the left-hand side. But before we integrate, let's not forget to plug in our definition of mu, and mu is simply x squared plus 1 to the 1/2 power. And the antiderivative of the left-hand side is very straightforward. There's really nothing to integrate. It's just the integral of this differential operator, which is simply going to be x squared plus 1 to the 1/2 times y. Now, there is an integration constant here, but we're not going to include it. We will include it when we evaluate the right-hand side, and the integration factor on the left-hand side can be absorbed into the right-hand side. Oh, maybe I forgot to mention. There's also an integration constant with the integrating factor, but we don't include it because it'll cancel out anyway, which explains why there was no plus c when we evaluated mu. Excellent. Now, on the right-hand side, we have a similar situation. It doesn't seem like we readily identify some kind of antiderivative on the right-hand side, but we can employ some kind of u substitution, and we could call u x squared plus 1, and du is 2x dx. Now, this is the exact same thing as before. It's the same u substitution. It's the same definition of dx. So we could directly plug that in just like we did before. And we can manipulate this a little bit. We see that the x's cancel out. We could pull out a 1/2. And now we have an antiderivative that we could readily evaluate because we could simply just use power rule, the power rule of integration. Now, when we apply power rule, we see that we end up with the antiderivative of u to the minus 1/2 power is simply just 2u to the 1/2 plus c, which should be pretty straightforward. And now what we could do is we can multiply the 1/2 on the right-hand side with every term, and the 2 cancels out. And then we could redefine our constant as lowercase c. So lowercase c is simply just uppercase c times the 2. Great. Now we're almost done with the problem, but let's not forget our original differential equation was in terms of x and y, not in terms of u. So we have to then plug in our definition of u, which is x squared plus 1. And now that we have that, the next step would be simply to just isolate y, and we could do that very easily by dividing by the x squared plus 1 to the 1/2 power on the left-hand side, and we end up with this equation here. And the middle term just reduces to 1 because the numerator and the denominator cancel out, and we're left with this final form. And this is the solution to the ordinary differential equation. Don't forget to like, subscribe, and support my channel so I could keep making videos.